Yeah, thanks, Lutz, for organizing it, and welcome all to the ISMC webinar. And today we have Paolo with us, so I will have a brief introduction, let's say, to Paolo. So Paolo Nasta is a researcher at the University of Naples, Federico II. He is an environmental scientist with expertise in different areas, including hydraulic engineering, soil physics, and also ecohydrology. And he's currently focusing on determining the soil hydraulic properties and the simulation of water flow and solute transport processes in the soil plant atmosphere continuum at the different spatial scales, but also on the assessment of human impact on ecosystem services in river basins in different environmental conditions and geographical areas. And thanks to Paolo's outstanding contribution to the understanding of flow and transport processes in soils, he's awarded Van Genuchten Award 2024. And thanks a lot, Paolo, for accepting the invitation to do the webinar today. So, Paolo, the floor is yours.
Okay, thank you, Eugene. I thank very much everybody from the ISMC. It was a very, very nice conference. It was well organized, and we enjoyed to participate into the conference where we had also Rian online. So he was connected during the dinner in the evening. So we really enjoyed his presence, and I was very, very happy, but also very, very honored to be awarded with the Van Genuchten Award. So for me, it is a pleasure to make this presentation for the ISMC. This presentation is about the past 20 years in the Alento Hydrological Observatory, where I carried out my main research activities, starting from my master thesis up to now. And then in the end, we can conclude by, let's say, by saying something on what's going on in the next 20 years. So we are going to present challenges and perspectives. So this picture is taken from the dam of the Alento catchment. This is the lake, the water reservoir, and this picture was taken from by Sarah, that participated to the Galileo conference in June 2023, last year, and we enjoyed very much the conference and the interesting discussions among the participants. So a bit before presenting, I want to say a couple of words on myself. So I got my master's degree in 2005 at the University of Torino in the northwest part of Italy. Then I moved south to Napoli for a 3 years PhD program under the supervision of Nunzio Romano. And after I got my PhD, I moved to a beautiful city in California, which is Davis, under the supervision of Jan Hopmans, and I met very smart guys like Irka Simonek, Jasper Frugt, in a 2 years postdoc. Then I moved to Nebraska for other 2 years, Lincoln, Nebraska, in the middle of US, with John Gates and Vitaly Zlotnik. And then I moved back to Napoli in 2014 up to now. So this is a sort of gross picture of myself. And this is why we started our research activities in the Alento catchment. But before introducing the Alento, I want to jump into the concept of a critical zone. So why the critical zone is so important? And this is important because it represents the outermost layer of the Earth, connecting the bedrock with the canopy. And most of the hydrological processes happen in this domain, in which we have to characterize the water dynamics and everything that is related to the water dynamics. So solute transport, heat transport, contaminant transport into the VADO zone up to the groundwater table. And so this is very important. And so this is why we want to organize the observations. And for instance, and this is why we establish critical zone observatories. So in the barcode, you can connect to a very nice video organized in US. And so you can have a look in this interesting video after the presentation. The research questions now in these days, in these years, are related to the rapid changes in climate, but also in land use that represent the anthropogenic disturbances that integrate the natural disturbances. For instance, drought, of course, is a natural phenomena, but is exacerbated sometimes by global warming in many areas of the world. But also we have fires, contaminant transport, land use changes that in few decades determine different land use maps around the world. And so the main research questions in these days are question about the impact of anthropogenic and natural disturbances on the ecosystem services related to the hydrological cycle into the critical zone. And so it is very, very important to gain a deep understanding of the water dynamics and all the cycles that influence the water dynamics. So I'm thinking about biochemistry, biochemical cycles and so on. And they have an influence on the hydrological behavior of our system. And so for this reason, we jump into the concept of a terrestrial observatory or just hydrological observatory. So in order to model, this presentation is for the ISMC, and the ISMC people are interested in modeling, but modeling without data is impossible. So there is a mutual relationship between data and observations, and we must focus first maybe on the observations, and that's why we establish and set up the terrestrial observatory, in which hydrology is one discipline in the interdisciplinary approach, or just hydrological observatories, in which we are interested only in the hydrological cycle. But this is very important because we must take into account in the future of several facets related to the ecology, for instance, biochemistry, hydrogeology, meteorology, and so on. And for this reason, I was mentioning that there is a mutual relationship between observations and modeling. There is a very nice plot at the top in which model performance depends on data availability and model complexity. But model complexity can be implemented only if we have enough data availability. And so we can reach satisfactory or high model performance. On the contrary, if we have a few data, because we don't have enough observations, maybe we can resort only to very simplistic modeling. And so we can simulate lumped response of our system to, for instance, to climate forcings. We are in the era of big data. We are in the era of artificial intelligence. So now the challenge is to make synergistic interactions between human expertise and artificial intelligence, because now we have huge and rapid technological advancements. We have machine learning, digital twins, Internet of Things, and many other tools that allow us to really go deep into the understanding of the hydrological behavior of our system. So we have great opportunities nowadays, and we have a lot of work to do in the next years, I think. And that's why we jump into the Alento Hydrological Observatory, which is located in southern Italy, in the administrative region of Campania. It's 2 hours drive from Napoli. The Alento catchment is 400 square kilometers, and in 1995 a dam was built in the middle of the catchment that separates the upper part, delimited by the black border, from the lower part, delimited by the red border. So the upper part is 100 square kilometers, and that's where we focused our main activities in the last 20 years. So we started with a historical site, symbolized by the red circle, called MFC1, because it's close to the town of Monteforte Cilento. And we started in 2006, and we ended up during my master degree, and we ended up more or less in 2011. So this is an historical site. I'm not going to mention our research activities there, but I'm open to share the data and to discuss after the presentation if you're interested. But the main research activities now are in the other 2 experimental areas, MFC2 and GOR1. MFC2 is the yellow circle. GOR1 is the blue circle. So they are representative of different environments in the same catchment. MFC2 is representative of agricultural use, agroecosystem land use. The soil is very has a high percentage of clay content. It's on the south face hill slope of the catchment, and it has a shallow aquifer. On the contrary, GOR1 is more representative of the catchment because it's covered by a dense forest of chestnuts and oaks. The aquifer is very deep, because at least 40-50 meters below the soil surface, and is more representative maybe of the current situation of the upper Alento River catchment. So in 2016, we started the collaboration with the Institute of Jülich in Germany, especially with Aje Bogena and Harry Verreken, that provided us 2 cosmic ray neutron sensors, SoilNet wireless sensor network, and we integrated these tools with our sensors, so weather stations, stream flow sensors, piezometers, and many other things. And that's how we started to establish the Alento Hydrological Observatory. If you want more details, you can read the publication in Vadozone Journal in 2018, where there are like many details on the Alento. It has, of course, the Alento Dam is the main site where we collect a lot of information, but especially the water level and also the precipitation in a weather station that was installed nearby the lake. And so you can see here the water level monitored every day since 1995. So you can see that stabilizes up to 1996. And then you see the typical fluctuations of the water level influenced by the typical seasonality of the Mediterranean climate. So you can see that the high water level situations happen during the rainy season, which corresponds to the winter, late fall, and they are alternated with very dry situations in summer, when the weather is very warm, hot, and dry. You can see that also there is a kind of normal fluctuation, but you see that, for instance, in 2017 we were hit by a prolonged drought spell. But ironically, in 2018 we had a very wet year in which we had also episodic overflows of the income flux. And you can see also some other episodic overflows in other situations. Another question was related to the impact of land use change on the water balance and soil erosion. So because we had the availability of land use maps, of historical land use maps, especially in 1955, where you can see the complete dominance of agricultural cropland. And then there was a transition period in which there was abandonment of the environment, and then up to nowadays, 2015 or even most recent land use maps indicate the full domination of the forest. So we wondered, what is the impact of this very rapid land use change on the water balance? And so we used the SWOT model, which is very adaptive to this kind of catchment, especially on the size of the catchment. And more details are given in this publication in 2017 in the Science of the Total Environment. Now, our philosophy is to organize the new observatory in the two experimental areas by integrating different observation platforms. So we want to exploit information from remote sensing products, from environmental tracers, especially stable isotopes of water. We have the capacitance sensors and cosmic ray neutron sensors. We carried out a spectral analysis in the laboratory and in the field, and also by using spectral cameras mounted on the drones. We determine soil physical, chemical, and hydraulic properties in the lab. So we organize several field campaigns. We go to the field, we collect soil samples, take to the lab, and run experiments, the conventional laboratory experiments, especially to determine the soil hydraulic properties, namely the water retention function and the hydraulic conductivity function. Finally, we also carried out several field campaigns of geophysical surveys in order to understand what's going on into the deep part of the critical zone. So this is our philosophy. We are trying to, it's been quite a few years that we are trying to integrate all these kind of tools through collaborations. So Eugene is also came to the field, but many other scientists from different disciplines came to visit the Alento Observatory. And so these are the two experimental sites located in the Alento catchment, so MFC2 and GOR1. So you can see that we installed, you can see the position of the cosmic ray neutron sensor with the white triangle in the middle. You can see the positions of the SoilNet wireless sensor network. We have 20 units with capacitance sensors and soil metric potential sensors installed at 15 centimeters and 30 centimeters. You can see also the streamflow sensor. You don't see the positions of the 20 piezometers installed in MFC2 to try to understand and monitor the water circulation in the shallow aquifer, which is about 2 meters below the ground, but sometimes in winter can come up to the surface. You see also the position of the isotopic measurements in the soil and plant tissues. And in GOR1, you see the equivalent equipment organized into the forest. So all this equipment allowed us to characterize the first results in terms of soil water content. So you can see the two plots showing the response of the system in terms of soil water content, at least near the surface, given the daily precipitation and the potential evapotranspiration data. And so you can see 3 lines in plot B, where you can see the green line, which is the area average soil water content measured, monitored by the cosmic ray neutron sensor. But you can see also other two lines, a red line and a black line. So the black line is the spatial average soil water content by using the factory calibration, while the red line, it's our own calibration that took into account also for soil temperature effects. And so I underscore the importance of calibration on the cosmic ray neutron sensor. So we ran several field campaigns around the cosmic ray to calibrate the cosmic ray, but also we ran several campaigns for the field calibration, but also we ran a lab calibration for the environmental sensors controlled into the SoilNet units. And so that you can see the importance of calibration, and this must be taken care of, especially in soils with high clay content or loamy soils, because this is the case into GOR1. Also, the isotopic campaigns, we carried out 2 years of isotopic campaigns every 2 weeks, so fortnightly. We sampled plant tissues and soil matrix at different depths, up to 1 meter. Then we extracted water in the lab by using the cryogenic vacuum distillation, and we measured the isotopes of stable water, especially the deuterium and oxygen 18. And so you can see on the right the dual isotope plots and mounted in MFC2 and GOR1. And you can see the typical local meteoric water line. You can see the fractionation effects on the xylem water, which corresponds to the water extracted from the plant tissues. You can see the fractionation effects also on the soil matrix near the soil surface at 15 centimeter. And then you can see the mixing effect in the groundwater and stream flow water, which suggests maybe the hypothesis that the stream flow derives from the base flow. And so we have to characterize the groundwater circulation, at least in MFC2. In GOR1, I remind that we cannot monitor the groundwater table. But we asked ourselves, so what we can do with this information? Because measuring the tracers is very interesting, because you can trace the single parcels, water parcels across the soil profile. So we wondered, so what can we do with isotopes? So our first idea was to estimate the temporal origin of drainage and transpiration water. And so that's why we tried to understand the impact of soil properties, soil layering, the soil characteristics, the plant characteristics, the impact of climate forcings on the movement of water into the soil profile. And for this reason, we started by using HYDRUS 1D to estimate the travel time originating from each individual rainfall events. And so in this publication, we share a MATLAB script implementing repeated simulation of HYDRUS automatically. So, because it's very time consuming, so we don't reduce calculation time, but at least we automate the calculation, so nothing is manual. So if you go to this link to this paper, in the supporting information, you will find a script in MATLAB that runs HYDRUS automatically for each rainfall event. And what is the advantage of estimating the temporal origin for each rainfall event is that we can estimate not only the travel time for drainage and transpiration, but we can couple the travel time to the rainfall contribution to drainage and transpiration. And we can also aggregate this information on a desired temporal resolution. So for instance, we can aggregate this information at monthly scale or at seasonal scale, whatever the season is, if it's the hydrological seasons or the typical seasons of the year. Another source of information is given by the geophysical measurements that we are carrying out on a seasonal basis in both experimental areas. So in this case, we show an example of geophysical measurements at MFC2 in two different seasons. So on the top, on the plots on the top, you can see the measurements in the wet season in February, in very humid conditions. In the bottom plots, you can see the measurements into the dry season. And so you can see very dry conditions. But the most interesting thing is to see the difference also in the spatial domain, both in the vertical sense, but also in the horizontal domain. And so you can see that there is a lot of spatial variability because the three plots go from the left to right, from shallow soil depths to more deep soil profile, but we are able to measure up to a depth of 6 to 7 meters below the ground. And finally, our main strength is in the soil sampling, because we are our specialty is the soil sampling, the determination of the soil properties. And so we designed a grid of almost 200 points in which we carried out spectral measurements, and also we sampled undisturbed soil cores to determine the water retention function, the saturated conductivity, the unsaturated hydraulic conductivity, and all the physical and chemical properties, so like bulk density, organic carbon, soil texture, etc. And so what can we do with all this information? So we know that the spectral measurements are rapid, fast, cost efficient, and so we do hope that we will have the opportunity to generate new spectrotransfer function in order to use the spectral measurements to estimate the soil hydraulic properties that you well know that they are hard to measure, they are time consuming, tedious. It's very hard, especially in the summer. You go to the field, you dig the soil, and it's very hot. There are like mosquito bites on your neck. And so you do hope really that new tools will come up in the future, or maybe are already available. And so we started from the spectral measurements that are very, very rapid. So you just need a few grams of disturbed soil samples, you dry the samples, and you carry out the laboratory measurements by using spectroradiometers, for instance. You can use also portable devices on the wet soil samples, but you can also mount hyperspectral cameras on the drones, so you can extend the information over large areas. And of course, there is a hierarchy of measurements, because we can integrate these measurements with aircraft measurements, but also, of course, with satellite products. And so there is still a lot of investigations to do in order to characterize the spatial variability of soil properties over different spatial scales. And the final target of using the spectral measurements, of course, is to map. So to use the spectral measurements in a dense grid of points, then implement the spectrotransfer function, so the STF, in order to generate a high resolution map of the soil hydraulic properties and exploit this map into a 3D Richards-based hydrological model, a process-based hydrological model. For instance, we use hydrogeosphere, but many other models are available, such as Parflow, etc., to simulate water flux and solute transport in each pixel. So this was our target 20 years ago, because below I report what we measured with the portable TDR Tektronix in 2006 and 2007 during my PhD thesis. So we measured in each pixel the soil water, the near surface soil water content, and we wanted to compare these observations with model simulations, and now it's possible. Now it's possible because new 3D generation models have been used for many years now, and so it's possible to compare the spatial distribution of soil moisture and other fluxes because we are measuring many other things. And so to conclude, challenges and perspectives. So the integration of different monitoring platforms is the key. So as I said, the relationship between observation and modeling is the most important thing for our research in hydrology. And it's growing up, advancing and progressing because of technological advancements. And so I think that in the next 20 years, we will have huge opportunities to extend our observations in the horizontal domain, but also in the deep domains of the critical zone. And we will have the opportunity to build, for instance, new dynamic vulnerability indicators at different spatial scales. We mentioned, for instance, the travel time, but it can be also the soil water, the soil water storage, for instance. All these vulnerability indicators can be mapped into large territories to indicate, to identify vulnerable areas, and to propose adaptation options to climate change, land use change, heavy contamination, and more and more. And so this opens new opportunities and new perspectives, also because our research strategy, but also our research philosophy in Napoli tries to combine different approaches, different disciplines, and to build let's say, a more complex knowledge, understanding to run more complex and refined modeling. The truth is that, of course, without data, we cannot do anything, but we need more and more data to do, and more details are given in the EGU blog, which was presented a few years ago. That describes our research activities in the Alento. I want also to advertise for the ISMC community that me and Nunzio Romano are organizing a webinar. The date has to be scheduled yet, so because we want to challenge students, master students, PhD students, with the basic concepts in soil hydrology, because then a couple of months later, we want to organize a summer school on the critical challenges in the critical zone. And so we want to invite students in Napoli, in our field, in order to apply what we learned in the field and also by using models. And so this is our, of course, when we have more information, we will share it with the ISMC community. And so I report all the references that I mentioned during the presentation, and I finished. So thank you very much, and I'm very happy to reply to your questions.